Let's look at more limits at infinity, this time involving roots. Square roots, cube roots, etc. Limits at infinity with regard to roots. And we're going to look at the algebra behind this, not so much the graph aspect of it. All right? So I will assume that you already know how to do some limits at infinity with basic ratios, ratios of polynomials or things like that. Here we're going to look at ratios that might involve roots. So let's say the first example that we want to work out is the limit as, actually, let me back up just a moment, I apologize. Let's lay some groundwork for roots first, right? You got into this calculus business and you thought you understood things like absolute values and roots and all that, and you very well may. But upon further inspection, sometimes these things are more cryptic than we originally thought. So I want to decrypt some of the information behind roots. So what's interesting here is if you look at odd indexed roots, in other words, cube roots, fifth roots, seventh roots, any odd root, they're the easiest to work with. And the reason for that is many things. For example, if you want to take the cube root of 8, it's no problem, it's 2. If you want to take the cube root of, let's say, -8, hey, that's also no problem, that's -2. And I'm not going to do a lot of examples there, this is pretty basic stuff, but the idea is if you've got an odd root, so this applies for fifth roots, seventh roots, etc. If you have an odd root, you can certainly have a radicand, the number underneath, that's positive, and you'll get an answer. Or you could have a radicand that's negative, and you'll still get an answer. Furthermore, your answer could be positive, or your answer could be negative. In fact, if the radicand's negative in an odd root, the answer is negative. If the radicand's positive, the answer is positive in an odd root. Isn't that nice? It works so nicely, okay? So the nice thing about this is when you get to variable radicands, for example, if you have the cube root of x to the third power, let's do that first. The cube root of x to the third power, well, it behaves exactly like you would expect. The cube root of x to the third is just x, no problem, it's that straightforward. Furthermore, if you look at the cube root of x to the sixth power, well, that's also no problem, that's x squared, just straightforward. If you have the fifth root of x to the 75th, no problem, it's x to the 15th, because it would take 5x to the 15th multiplied together to give you x to the 75th. Odd roots, no problem. Even roots, all kinds of problems. So let's start to distinguish even roots. The nice thing about odd roots is you can input anything you want, and they can output positives or negatives. It doesn't matter. The problem with even roots is they're really persnickety when it comes to negatives. And I'm not going to get into why. You should already know that part. But for example, if I say the square root of positive 4, that literally means the positive square root of 4, which is positive 2. Of course, 4 has more than one square root. Negative 2 is also a square root of 4. But when we use this symbol, it literally means the principal square root, or the positive square root only. So even roots, what we should see is they result in, I can't say positive answers, but I can say non-negative answers. Okay? I can't say positive answers because the square root of 0 is 0, which is not positive, but it is certainly not negative, right? So that's just a semantics type of thing. No big deal. Okay, so the other thing is, what if I want to know the square root of -4? Well, the square root of -4 involves the imaginary number I. And when we're dealing with functions and basic algebra, basic calculus. We're dealing with functions that deal with real numbers only. Okay, so we need to avoid this type of thing. So not only do even roots result in non-negative numbers, even roots are really averse to negatives, right? It results in a non-negative answer, but also you better have a non-negative radicand. They have all these demands, right? Square root says, only feed me non-negatives. I'm only going to give you non-negatives back. And that's it. No questions asked. That's all I'm going to do. So we just have to be careful with these guys. So for example, if I have something like the square root of x squared, boy, wouldn't it be so nice if that were just x? It would be nice, wouldn't it? The problem is, what is x? It's a variable. What does that mean? It means that it could take on any value. It could be a negative number. It could be a positive number. It could be 0. So if you just remember that even roots result in a non-negative answer, that can help you tremendously. So first things first. If x were negative, is it okay for x squared to be our radicand? Well, in the case that x is negative, x squared would be positive. Well, that satisfies the square root because he only likes to take non-negative inputs. So x squared is not a negative number inside the square root, so he's happy with that. Now, the partnership we have with the square root is that he's going to give us back a positive or non-negative answer. And right now, since we don't know what x is, x could be negative. And so the square root of x squared may not equal x because x could be a negative number. So what we end up seeing is, when does the square root of x squared actually output x? Well, it outputs x. Hey, it outputs x if x is not negative, right? So in other words, if x is greater than 0 or equal to 0. So you might ask, what does x squared output if x is negative? Well, it's no big deal. How can I make x positive if it's negative? I just attach a negative in the front of it. So the square root of x squared actually outputs the opposite of x in the case that x is negative. Now the equals to could go on either one of these. It doesn't matter. I typically like to associate it with the positive, so those are my non-negatives and then these are my negatives, but it doesn't matter. The point is the square root of x squared has this sort of ambiguous output because we don't know what x is by definition, so it could be one of two answers. And this is true for all even roots. So let's look at the sixth root of x to the 18th. It's an even root. The answer better not be negative. So we ask ourselves, is it okay for the answer to be x to the third? The answer is no, because if x is negative and we cube it, this is a negative answer. So we get a similar type of idea here. In this case, the sixth root of x to the 18th could be x to the third. It certainly could be, but when? Well, it's the answer you'd like whenever x is not negative. It's the opposite of that answer if x is negative. Okay? So kind of tricky. You want to throw another kink into things? I think we can do that. Let's suppose that we have the fourth root of x to the 8th. You would expect that to be x squared. Is that an okay answer? Well, we need this thing to output something that's not negative. And regardless of the value that x takes on, x squared is certainly not negative. So in this case, we're good. The fourth root of x to the 8th is always x squared, whether x is negative, positive, or even 0. So the issue becomes when the output of these have odd powers, x to the first, x to the first, x to the third, x to the third, you have to sort of distinguish what the output is. Okay, so that's some background about square roots. I tend to go on about it, but I feel like this is not as, it is a simple concept, but I like to hit things deep, make sure we've got it before we progress. So let's progress. Okay, let's do some limits. How about that? That sounds like a good idea. Let's say that we want to take the limit as x goes to infinity. Notice that as x goes to infinity, we're talking about positive x values. Keep that in mind. As x goes to infinity of this ratio, and on top we've got 1 minus 3x plus 4x to the 6th under square root. And on the bottom, we have 6x to the 3rd minus 2x squared plus 1. Okay, so if we think about evaluating this limit as it sits, we'll see that, well, the highest power on top is x to the 6th, which as x goes to infinity, that turns into positive infinity and dominates all these smaller powers of infinity. So we've got the square root of infinity on top, which is infinity. And on the bottom, the x cubed dominates the other smaller terms. As x goes to infinity, this turns to infinity. So we've got infinity over infinity. Can't evaluate the limit as it sits. So we employ the strategy we learned with rational functions where we try to make a constant into the highest powered term on the bottom, the highest degree term on the bottom. So the way to do that is to multiply the top and the bottom by 1 over x cubed. Or divide the top and the bottom by x cubed, however you want to think about it. And so it's easy on the bottom, right? So the bottom, we end up getting the limit. And when I distribute, I get 6 minus 2 over x plus 1 over x to the 3rd, okay? On top, I have a problem. All of this is under a square root, and this guy is not. I need to make them compatible for multiplication. So what I need to do is I need to turn this guy into a square root so he can be friendly with this square root. So let's discuss 1 over x cubed as a square root. Well, as a square root, it turns into 1 over x to the 3rd is going to be something like the square root of x to the 6th, okay? The question is, do we need to include a negative in this because of all the discussion we had before? So the square root of x to the 6th, we want to know, does that equal x to the 3rd or negative x to the 3rd, right? Well, in this case, x is positive. So x to the 3rd is positive. So we don't want the negative x to the 3rd. The square root of x to the 6th is x to the 3rd. So we can literally call 1 over x cubed this guy. So let's do that. So on top, we're going to consider this ratio as a square root to make it compatible with the square root. And on bottom, we're going to leave it alone because it's already compatible. But on the top, what we see is we end up with the square root of 1 minus 3x plus 4x to the 6th over the square root of, right, we're multiplying this ratio by the square root. So we're dividing the square root by the square root of x to the 6th. And now this is compatible to divide. And so what we get is the limit. On top, I get this big square root. So I get the square root of 1 over x to the 6th. Right, everything's housed under a square root, so I can do this. Minus 3x over x to the 6th. So this x cancels with, if you're confused by this, what we're doing is we're simply housing all of this under one big square root, right, like this. Because that's how you divide two square roots. So I've got 1 over x to the 6th. Negative 3x over x to the 6th turns into negative 3 over x to the 5th. plus 4x to the 6th over x to the 6th just turns into 4. And my denominator is still 6 minus 2 over x plus 1 over x cubed. And we're taking the limit as x goes to infinity. And so when we do that, these guys go to 0, my favorite part. And so what remains is on top, I've got the square root of 0 plus 4, so the square root of 4. And on bottom, I've got 6 minus 0 plus 0, which is 6. So I've got 2/6 or 1/3. Okay, so that limit is 1/3. All right? I'm going to do the same limit. Now you may, if you want, you might want to pause the video and rewrite the problem and pause as I go to rewrite. But all I want to do now is look at what happens differently. I'm going to change the problem and rework it using what I have here because not much changes. But as x goes to negative infinity, we still have the problem of this indeterminate sort of idea. And I still need a constant 6 here, so I still use 1 over x cubed on the top and the bottom. The difference comes when I'm analyzing how to turn x to the third into a square root. So now, when I'm doing this, the square root of x to the 6th needs to be positive. So I'm asking, is it x cubed or negative x cubed? Well, now x is going to negative infinity. So x values are negative values themselves. So if x is negative and I cube it, I get a negative answer, and a square root can't have a negative answer. So now I'm looking at this guy. So in other words, this x cubed, right, I'm wanting to replace x cubed. X cubed is the opposite, right? If I multiply both sides by -1, this turns into positive x cubed, and that turns into the negative square root of x to the 6th. So now all that's going to change is 1 over x cubed is the same thing as 1 over negative square root of x to the 6th. So if we come back in here, again, pause if you need to so you can copy down what you want. Let's see here. I'm breaking whiteboard rules here, right? I'm not supposed to use my finger to erase on a whiteboard. So I have on top the same square root, and now on the bottom I've got negative square root of x to the 6th, which is different. I didn't have this negative here before. When I divide the square roots. Divide the square roots, so everything is housed under the square root except for that negative, right? I had a positive square root divided by a negative square root giving me a negative answer that is the square root. And then all that does is carry down the negative, and then everything else is the same. All of these still go to 0. This is negative square root of 4, so this turns into -2, which makes this negative 1/3. So that's the difference. When you're converting these ratios to square roots, you've got to decide, does it equal the square root you expect, or does it equal the opposite of the square root based on the x values that are represented in the limit? All right, good. Let's do one more example, and we'll call this video done. So we'll kind of look at one that works out unexpectedly. Let's look at the limit as x goes to negative infinity. Let's do another one where x goes to negative infinity of the square root of x squared plus 2x plus x. So there's no ratio here. But when you look at evaluating the limit, you end up with, well, you plug negative infinity in, and when you square negative infinity, you get positive infinity, and that's going to dominate this guy. So we've got the square root of positive infinity, that's infinity, plus negative infinity. So we have positive infinity plus negative infinity. Again, some infinities are bigger than others. So infinity minus infinity is also what we call an indeterminate form, because we don't know which infinity wins that battle. So we have to try to come up with some way to determine what happens here. Well, the common technique when you have a square root plus or minus something, and you can't work it out as is use what's called the conjugate. So that's what we'll do here. So this is going to equal the limit as x goes to negative infinity. And we're going to turn it into a fraction. That sounds like a great idea, right? Said nobody ever. It's over 1. Now, if I use the conjugate, I'm going to use the conjugate to try to rationalize that numerator so there's no square root. So what that looks like is I'm going to multiply this ratio now by the conjugate of the numerator. So it's the same thing, but with a minus instead of a plus. And if I do it on the top, I have to do it on the bottom as well. Okay. The good news about conjugates is they're easy to multiply. Not going to spend a lot of time on that part. We have to multiply all of this by all of this. So the square roots, when you multiply a square root by itself, it goes away. So you just get x squared plus 2x. And then typically when you distribute, you would do this guy and this guy. But because they're conjugates, those two terms end up being exactly the same, but one's positive and one's negative, so they cancel. So all that's left is positive x times negative x, which is negative x squared. So that's our numerator, no more square root. It's been rationalized. The denominator, I take 1 times this mess, which is just the mess. A mistake that I see students make all the time here is they get careless with the radical symbol. The square root here applies just to the x squared plus 2x. If you make the mistake of carrying it over the minus x, it causes huge problems. So be really careful with your radical symbols. All right, and before we try to evaluate this limit, let's see what happens. X squared minus x squared is 0, so we just have that. Okay, now let's think about the limit. When x goes to negative infinity, 2x goes to negative infinity. When x goes to negative infinity, we get positive infinity, and we get minus negative infinity, which is positive infinity. So on top we had negative infinity, on bottom we have infinity plus infinity. We've still got this mess of infinity over infinity of subtype. So we've got to do more work. So what we do is we look at the bottom, and we look for the highest power of x. Well, we have an x squared. Don't be confused, it's not really an x squared. It's an x squared hiding out inside a square root. So it's really like an x, because the square root of x squared is x. So we have an x term and we have another x term. We can sort of eradicate both of them because they're both x to the first power concurrently. So what we're going to do is we're going to multiply the top and bottom by 1 over x, because that's the highest power we see down here. The top is simple. We get the limit. 2x divided by x is just 2. The bottom is a little trickier because I've got this minus here, so I have to distribute my 1 over x to the square root. So I'll have x squared plus 2x under the square root, and that's over x. Again, don't drop your radical symbol down below the fraction. I'm dividing the square root by x. The x is not going inside the square root. And then 1 over x times negative x is negative 1. Okay? And now we have to sort of clean this stuff up. Right now this x is not compatible with the square root. So again, using what we know from before, x is going to negative infinity. So we're talking about negative x values, which means that x is the same thing as not the square root of x squared, but it's the same thing as the negative, let's write this out. In this case, x equals the negative square root of x squared, because the x values we're dealing with are negative. And now I can divide these x squareds and this 2x by x squared. Sort of inserting the x squared under that square root altogether, and then keeping the negative. So on top I've got 2. On bottom I've got negative, and I've got this big square root. X squared divided by x squared is 1. 2x divided by x squared is 2 over x. And then I just carry down the minus 1 here. Finally, let's finish this off. As x goes to negative infinity, this ratio goes to 0, and we end up with, on top we have 2. We've already applied the limit, so I don't write the limit anymore. 2 over negative square root, 1 plus 0 is 1, minus 1. So on top I've got 2. Well, the square root of 1 is 1, so then I've got negative 1 minus 1, which is negative 2. 2 divided by negative 2 equals negative 1. So there's a lot going on here. We couldn't evaluate the limit as it sat, so we turned it into a ratio so we could rationalize. We knew to do that because we had a square root plus something, or in the case of a square root minus something, you might try it as well. And then what we ended up was with an indeterminate form again of infinity over infinity. So we had to utilize what we knew about ratios. And to make this x compatible with the square root, we had to utilize this concept again. And then we used what we knew about limits of these little ratios going to 0 to finish the problem.